Okay, I'm going to attempt something that I've often thought I should try to attempt, is doing a quick sheet on what's called alloy equilibrium diagrams. Okay, so I suppose the question is, what are equilibrium diagrams? So So what can you tell or find out from them is basically they're thermal, to do with heat. Okay, so we'll say that's the first thing. And two, it gives you the temperature that a metal melts and solidifies. And then when you have an alloy, the temperature that the different mixtures melt and solidify it. Okay, so that's some of the stuff that you can find out from an equilibrium diagram. So I suppose the first place I want to start anyway is, like, how do you show information about a metal melting on a diagram? So one really simple way of doing it is just saying, look, if I heat a metal up, and let's say the metal melts at 180 degrees C, and then I heat it up more. Okay, so this is 0 degrees and this is, 180, it melts. So it's solid down here and it's liquid up there. And let's say now 180, let's say that's 280 degrees up here. Okay, now all it is there is just a hotter liquid. I mean, once it goes above its melting point, it's solid, getting hotter, then it melts, and then it just becomes a hotter liquid. And could it ever evaporate? Apparently it could in a nuclear war, but anyway, so like that's a really simple way of explaining what happens to a metal when you heat it up and showing its melting temperature, which I'll add here. So that's the melting point there. But like that doesn't tell you, that tells you a little bit about a metal. All right, so it melts at 180 degrees and above that is liquid. But it doesn't tell you though more stuff there though, that like if we added time to it, okay, so let's say we took it a step further and we said, all right, let's put time into the equation. And here's our 180 degrees C. That's 0 degrees C. Okay, so we start our clock here, and let's say after, say, 15 minutes, and 30 minutes and so on, and 45 minutes and so on. So you turn on the clock and you start heating up the metal, and it's getting hotter and hotter and hotter and hotter, and then it reaches 180 degrees. Now what actually happens is it will stay at 180 degrees for maybe 15 or 20 minutes, depending on how much of the metal, how much volume is there. And when it reached 180 degrees, it would have been solid. It is melting as we go along here, and then when it's completely melted, it will heat up. Then you could heat it up hotter if you wanted. So that there now is called a time temperature diagram. Now, the things that you would want to know about that is that it is solid all the ways up to here, and then it's okay, it starts to melt here, completely melted here, and then it's just getting hotter and hotter as you heat it up, because you could continue heating it up. So that there is a time temperature diagram, and if I wanted to there, then you could say then, all right, so let's say we kept it at, or we heated it up, and then we kept it at a temperature of, let's say that was 280 or 300 degrees. So we kept it at 300 degrees for a while, and we start leaving it cool down again. So it's cooling down, cooling down, cooling down. When it gets to 180 degrees, it stays at 180 degrees for maybe 15-20 minutes, half an hour, until it goes from being completely liquid to completely solid. And then it starts to cool down again if you give it time, all the ways back down until it's cold, 0 degrees C, back down here again. So let's say that would be 45, 60, 75, 90, say 100 minutes or whatever. Like, the time doesn't matter. It depends on how powerful your furnace is and how much metal is there. But what I want to focus on is what's going on here. Okay, because what is going on here is it begins to solidify, and over here it is completely solid, and then it cools down again. So why does it stop heating up until it goes completely solid to liquid, and why does it stop cooling down for 15-20 minutes, half an hour, whatever, until it goes from being liquid to solid and cools off down again? And the reason for that, okay, so I'll ask the question, why does the temperature stay the same? Now, the answer is due to the latent heat, which means hidden heat of fusion. Okay, now basically, and it's important to just, I suppose, understand that what happens here is the atoms are, let's say if you're melting it, you heat it up hot and the atoms are vibrating and vibrating, and eventually the hotter it gets, the more they vibrate, until eventually they can break the bonds in the solid and become a liquid. And that kind of continues on there until all the extra heat goes into breaking the bonds between the atoms, and only when that's completed then can it continue to heat up again. So that's one thing that you kind of need to understand a bit. You know, it comes up, well, it's not that key really, but it comes up a bit. You get asked about time temperature, but time temperature information is what is used for drawing an equilibrium diagram. So one other thing there I will just touch on there is okay, what is an alloy? Because we touched on an alloy here. So an alloy is two metals mixed together. Okay, so a couple of the best ones, known ones there would be solder or brass or bronze. Solder would be lead and tin. Brass would be copper and zinc. Bronze would be copper and tin. Okay, so that's what an alloy is. And just put a tiny bit of color on this. Okay, a tiny bit of color on that. Okay, so alloy equilibrium diagrams. Now the word equilibrium means, and I'm going to write this down, equilibrium means slow cooling, allowing time for all changes. So I'll just say happen. Okay, so like you'd heat something up slowly and you'd cool it down slowly, well, particularly cooling it down slowly. Now the next thing I want to look at here then I want to look at there is when a metal goes from a liquid to a solid. Okay, so it's basically on the thing here, on our time temperature thing, this section here, what goes on when a metal solidifies. So the easiest way, I'll just put a heading there, solidification. Okay, so the easiest way to explain this is with four circles, really, one after the other, like this. So let's say that is liquid, completely liquid. This is completely solid. And these then would be what's called pasty, I guess. So in a liquid metal, you might have a couple of points there. If there was a speck of dust or dirt, or you could throw in talcum powder is used in steel to cause what's called nucleation. And so you've got liquid, and then you would have nucleation, where at some random points as a metal cools down, that would be at this temperature now, it just randomly begins to solidify. And even though the temperature would be staying the same, you would get then what's called here dendritic growth. So nucleation, and what that is you get these kind of needle spikes. They're called dendrites, but it's like frost on a windscreen. And you would get what's called dendritic growth of these spikes of solid growing out into the liquid. So you want to be able to show these things on a diagram to talk about, it's called green growth or nucleation, and nucleation and green growth. So they're getting bigger and bigger. So I'll stick a color on this in a second, until eventually the solid parts eat up all the liquid. So I'll just stick a color in here. Okay, so let's say the blue area there would be all solid, and as time goes along there, the solid part is increasing in size. So this is called green growth or crystal growth, until eventually then it's completely solid. And if you look through a metal at a metal through a microscope, that's what you would see there is crystals. I'm not sure now how clear that's coming out, so I'll just heavy that in there again. So you'd see crystals, so it's not all just one solid lump, would be made up of different crystals or grains that grow into each other. So that's solidification. So nucleation and crystal growth, and then it's fully solid. So all of that would be, let's say, stage 1. This would be stage 4. And obviously stage 2 and 3 would be along here, 2 and 3. But so you'd have nucleation, green growth, and completely solid. And then, even though this would be red hot now, this would be 180 degrees, then it would cool down to 0 degrees, but those grains would stay the same. So you kind of need to understand that kind of stuff as well, because it comes up in the exam question. So the next thing I'm going to look at there, and I'll just adjust my camera here a tiny bit. Okay, so I want to look at, there's generally 3 different types of equilibrium diagram. So you can have so I'll just sketch these out here. There's 3 different types of equilibrium diagram. Now, I'm not going to get caught up in temperatures and all that kind of stuff there, but I'm just going to say that you'd have generally 0% to 100% of one of the metals, 0%, 100%, 0%, 100%. Of generally they give you metal B, right? But there's 3 different kinds of alloy equilibrium diagram that we need to be familiar with. So the easiest one is what's called a solid solution. So I'm going to say 1, a solid solution. Equilibrium diagram. Okay, now in a solid solution, the first thing you need to be able to do in these questions is to label the diagram. So to label that diagram there, down here is solid. Okay, now let's say, you know, you'd have 0% B here, which means it's 100% A. I'm going to write that down just in the first one. So if it's 0% B, it has to be 100% A. So let's say if it was lead and tin, this might be no lead, so it's all tin, and this would be all tin, so it's no lead. But I'm only just going to do that on the first one now, because you only really need the two of them. It has to add up to 100%, so obviously in the middle would be 50-50. Okay, so the first thing you need to be able to do is to label these diagrams. Okay, and there's a couple of, always at the top, okay, because this is your degree C, so always your temperature is along the vertical here, and always it's liquid when it gets heated up a lot, obviously. So there's some obvious stuff like that. So that's our solid solution one. So that's solid when it's cold, liquid when it's hot, and pasty in between. That's very important to understand that basic stuff. Now, the second type of one we're going to look at then is called eutectic solution. Now, they always look like this. But again, you need to be able to label the diagram. So always up here is liquid, always down here is solid, and in here would be pasty. Now that's pasty, not pastry. It's not, don't be getting it mixed up now. It's something in the deli. So liquid, solid, pasty stage there. I know pasty is a mixture of liquid and solid. So some of it is liquid, some of it is solid. Now that so the last one here then is called partial solubility. Okay, equilibrium diagram. Now that is kind of a mixture of these two. Now I'll talk more about it in a second, but I'm going to just draw it first. But it's kind of a mixture of those two. So they look something like this. But again, up here is liquid, down here is solid, and in here would be pasty. Okay, so I'm going to talk later about these. I'm going to come back to these two regions here. Now, the next thing I want to look at then is you get asked the question there about there's the upper line here is called the liquidus line. Now, to colour it, will I colour it? I don't think I'll colour it, but I'm going to say there that this is called the liquidus. And this is it here, the liquidus. And over here, now it's pretty straightforward really. The liquidus line, anything above the liquidus line is 100% liquid. Okay, so that's what the liquidus line is. Above and obviously, you know, it means, you know, for any mixture 50-50, like a 20-80 mixture, whatever, once it gets above that temperature, it's completely liquid. Now, the next one I want to look at then, if I can find myself a colour, is the lower line along here then is called the solidus line. And below this line, everything is completely solid. So whatever the temperature is, okay, so like if I was talking a 50-50 mix, whatever the temperature here is, it's completely solid below that. So here's our solidus line. And over here, this is our solidus line. I'm going to just explain there that the solidus line is here. Maybe I will put this in color, it might help to understand it. Okay, so that's the solidus line. Below it is solid. Okay, and now that we're in coloring mode, here's our liquidus line. Above that is liquid. Now when you get asked in an exam to label the diagram, that's what you're being asked to do. And the liquidus line over here okay, so a solid solution, a eutectic solution, and a partial solubility. So that's the three types of diagrams. But the question is, like, why is there three different types of diagrams? And it basically depends really on what way the atoms have relationships to do with each other, a bit like GA supporters or soccer supporters or whatever. Is probably a good analogy, or you know, to use. So in a solid solution, both kinds of atoms are happy to mix. So and I'll just write there that both types of atoms happy to mix in both liquid and solid. Now, in the eutectic solution, it's different. The atoms don't want to mix in solid, so they form layers. Okay, so and finally the last one there is the atoms happy to mix I'll say mix or absorb a small amount of each other in solid. Now I'll come back to this in a while, okay? But so when I say a small amount, let's say maybe say 5% you know, I'll just ballpark figure 5% to 10%. Okay, but any more than that, any more, that means layers. All right, so how do you show that information there then, you know, on a sketch, which is the next thing we need to look at. Okay, so we said in a solid solution, and again, I'm going to just show two sketches relating to this now. So let's say we've got two different types of atoms here. I'll just go with, say, there's blue atoms and I'll go with orange atoms. Okay, so they are happy to mix. So what you do there is just make sure it's on the camera. It is. So if you had through a microscope and you were looking at crystals of a solid solution, you would have the two atoms. No, I could put this in dots, but I'd be forever doing it with dots, so I'll just put one in light, and I'll put this one then in dots. So the two, I'm using colors to explain atoms here, but they're mixed up everywhere. So it's a bit like going to a GAA match between maybe Cork and Kerry, and the supporters are mixed up everywhere. They're completely dispersed randomly, you know, all over the place. So that's how it looks like through a microscope, and you need to be able to relate that when it's solid. Okay. Now, the eutectic solution there then, let's say we were looking at a crystal through a microscope. Now, eutectic solution is different because the two types of atoms do not want to mix. So again, how do you show that in a diagram? So I'm going to put in just a quick way of showing this now, because you want to be able to explain this pretty quickly, is I'm going to show this with layers. So what they do is it would be a bit like, let's say, in a GA analogy, it might be like Tipperary supporters, that you'd have a row of them here and a row of them there. So the best way that they can find of separating themselves from everybody else would be to form layers. Let's say it was Tipperary and Kilkenny or Tipperary and Cork or whatever. So and finally there then, on the partial solubility, you've got two things going on. So because it's kind of a combination of the first two here. So I'm going to draw two circles over here. I'm going to draw a few crystals. Actually, I need three. So I'll just adjust that camera there a tiny bit. Okay, I'm going to need three different colors over here because I could have, no, this is called the solvus region here. I'll stick this in here now. And I was saying there earlier on that, like, let's say that's the solvus region and it's got a lot of one metal, let's say the orange metal there now. So what I was saying is it's happy to absorb a tiny amount of the other metal. So maybe 5% in solid solution, which means kind of evenly distributed. So I'm going to say, like with the blue ones there now, that it's happy to take a tiny amount of 5% maybe of the other metal into solid solution. It's happy out. Now, where you've got a lot of the other metal at the other extreme, then let's say this is a home match for Arma and this is a home match for Monaghan, going with our jade colours and stuff like that. But so when I draw our crystals here, again, this is mostly like you've got 95% of one metal here, and it's happy to absorb then maybe 5-10% max, probably, well definitely I'd say 15% max, but so it's happy to absorb a small amount of the other metal, but just go with 5% in your head, into solid solution. Now to get the exact figure, you just come down from here, percentage wise, that is the maximum that one wants to absorb, okay, that the Monaghan supporters want of the opposite, and so on. So this is your maximum percentage. Can be just read off the percentage down at the bottom of the diagram here. Now this video is kind of just to, you know, it's a summary of it. It's not sort of teaching it from scratch really. It's kind of intended for people that have it done before and just an overview of it. And in the middle then would be, once you go above that small percent, 5 or 10% that they're happy to absorb, but let's say it's 50-50 or 60-40, what you get then is you're back to this one, which is layers, that they, to get away from each other, the best that they can do is form layers, or like sitting in rows beside each other. So to show that on the diagram, that would be one crystal, and you need to crisscross these now just to make it kind of look realistic, to make sure all the greens look different. Okay, so this would be a solvus region coming from there, where you've got a lot of one metal absorbing a small amount of the other in solid solution. Solid solution being scattered all over the place, no problems. And the same with that's coming from the solvus at the other side. And finally there then, let's say kind of, I'll just say larger amount, okay, gives layers. Okay, and again there, this is layers because the eutectics, they don't want to mix solid solution, happy to mix in any amount. Now, just to go back to this one for a second, there is two ways you can have solid solution then. Okay, you can have substitution or interstitial. Now that depends on the size of the atoms. So let's say the atoms are in some kind of a pattern, and again, I'm not going to get too big into this here now, but atoms form patterns like based on cubes and hexagonal prisms and stuff like that. So a substitution would be where the atoms are both roughly the same size, and let's say one of the orange ones takes the place of one of the blue ones in their crystal pattern, whether it is FCC or BCC or whatever the patterns are. So that would be a substitution. Whereas it could be in an interstitial where one atom is bigger than the other. So you've got big atoms and small atoms, like in carbon, the carbon atoms are small and they go in between. So that would be an interstitial alloy where the small atoms of one metal go in between the bigger atoms of another. Okay, so that is basically in terms of sketching an understanding really of the three different types. So the solid solution, happy to mix in solid, whether it's by substitution or interstitial. Eutectic solutions do not want to mix, so they form layers to separate themselves, and the partial solubility is a mixture of both, where like it's happy to take maybe 5%, and when there's 100% of the other, well, it wouldn't be 100, then it would be like, it can absorb a certain amount of the other when it's solid. But note though, when it's warmed up, when it is warmed up, not when it's cold, it doesn't really want to have any, but as it's warmed up. So it's a kind of mixture of both of them. Now the last thing that I wanted to talk about there then, that I didn't touch on at all yet, is this special point here on the diagram, and that is called a eutectic point. And I'm just going to get a different color for that. So I'll just write, and I'll just adjust the camera there as well, maybe. Now I'll just write the question there. So what is a eutectic point? Okay, now this now links back up to what I was talking about earlier on. Generally, a pure metal, and we spoke about it right in the start, that a pure metal has an exact melting temperature, like, it could be 300 degrees or 167 degrees or 3280 if it's tungsten or whatever, but it has an exact melting point. But most of the alloys have a pasty range where, if I was heating up, let's say 20% of one metal there, it would begin to melt at this temperature and be completely melted at that temperature. So let's say, for 20% metal, let's say 20%, it would begin to melt at that temperature and be completely melted at this temperature. And if you kept heating it, then it's just a hotter liquid. But there is a special mixture in both the eutectic and the partial solubility. There would be one special mixture where the alloy, okay, I'm going to write this down. It is a special mixture where an alloy behaves like a pure metal. And has no pasty stage or range, I could use the word as well. The alloy has an exact melting temperature. Okay, so the eutectic point okay, why don't I just screw it up so that everybody can't read it? Okay, so eutectic point. Alright, I think underlining would have been a better strategy for that now. Okay, so the eutectic point anyway, just to show it's here and there, and I better label that as well. So the eutectic point is there and over here. Eutectic point. Okay, so basically all the other mixtures, you know, have a range, like it starts to melt at one temperature, but it's at a much higher temperature